हम लोग हाई स्ट्रेंथ डिफॉर्म्ड स्टील के बारे में स्टडी कर रहे हैं। IS 1786 2008 में इसके स्पेसिफिकेशन दिए हुए हैं। पिछले वीडियो में हम लोगों ने प्रूफ स्ट्रेस के बारे में स्टडी किया। प्रूफ स्ट्रेस द लो एलॉय कार्बन स्टील जो डिफॉर्म बार होता है लो कार्बन स्टील का होता है, जिसमें एक डिफाइंड यील्ड पॉइंट नहीं मिलता while doing the tensile test. To find out the yield point, we use the proof stress. Proof stress is nothing where the first deformation of bar take place. That is the point that junction is a yield point. So we know that when in the mild steel case, yield point occurs, and which is about 0.2% of the gauge length. So we determine the gauge length, which is 5.65 root A. Take the 0.2% of it, draw a parallel graph to the stress strain curve, and find out where it intersects to the stress strain curve, and corresponding stress is a proof stress. In the field, we can also plot load versus elongation graph, take the 0.2% of the gauge length, draw a parallel line to the stress strain curve. Wherever it bisects, from there take the yield load, that is P, and divide by its cross section area. We find out the proof stress. In this video, we will be studying about what is nominal sizes of the deformed steel bar, what is the mass per meter length, and what is tolerances given in the IS 1786. This is the deformed bar, say having 1 meter size, and this is the plain bar. If we take the plain bar of say 8 mm dia of 1 meter, 8 mm dia of 1 meter, it will weigh about 0.395 kg. So same dia will be the bar of deformed bar. That weight of 1 meter deformed bar should also weigh to the 0.395 kg. So this is given by the diameter of plain round bar having the same mass per meter as the deformed bar. So जो diameter of plain bar का हम measure करेंगे, which can be measured, so जो भी उसका mass per meter आएगा, that should be the mass per meter of the deformed bar also. Since we cannot measure the exact diameter of the deformed bar, so we go by the indirect method, which is also given in 6.3 clause of IS 1786. So nominal sizes of deformed steel are in mm, 8 mm, 8 mm, or we can start in the IS code. In the IS code, it is given from the beginning 4 mm, 5 mm, 6 mm, 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, 25 mm, 28 mm, 32 mm, 36 mm, and 40 mm. These sizes are produced by producers. If any special size is required, a special order is to be given by the purchaser. So all this is the nominal sizes available in the market for the use in field construction. Now I said that since we cannot measure exactly deformed bar diameter, it is measured from the indirect method. For in IS 1786 class 6.3, to measure the gross cross-sectional area, the formula is given: weight upon 0.0785 into length. Weight should be in kg, measured to the accuracy of 0.5%, and length should be in meter, measured in to the accuracy of 0.5%. So we get the gross cross-sectional area. The specimen length should not be less than 0.5 meter. 1 meter, preferable size is 1 meter, or if anything say 1.2 meter, 1.3 meter, we need to wait 1.2 meter, 1.3 meter. Same length, same weight we have to give here, and the length also. If say specimen of 1.2 meter, let us put 1.2 meter here, and the weight of corresponding put in the formula. So we get the gross cross-sectional area, gross cross-sectional area of the specimen of that size, whatever size was there. Say if we take 8 mm 1 meter length, or we take 10 mm 1 meter length, so we weight, so weight will be say 617 grams, and length is 1 meter, so weight will be 0.617 kg, length will be 1 meter, so we will be getting cross-sectional area of it, say 78.6 mm square. So this is nominal cross-sectional area of the mass, which is calculated by weight divided by 0.00785 into length. So nominal sizes, as we discussed in the previous slide, cross-sectional area in mm square, in mm, and mass per meter in kg. So nominal sizes are generally in the field we use 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, 25 mm, 28 mm, and 32 mm. So we will discuss about those sizes in this table. So nominal sizes are 8 mm, 10 mm, 12 mm, 16 mm, 20 mm, 25 mm, 28 mm, and 32 mm. The cross-sectional area we weight that to the precision of 0.5%. We find for 8 mm it is cross-sectional area is 50.3 mm square. For 10 mm 78.6 mm square. For 12 mm it will be 113.1 mm square. For 16 mm it will be 201.2 mm square. For 20 mm it will be 314.3 mm square. For 25 mm it will be 491.1 mm square. For 28 mm it will be 615.8 mm square. For 32 mm it will be 804.2 mm square. So all this calculation can be done by weight upon 0.00785. So this is the indirect method of calculating the diameter. Now we can calculate the diameter of the bar. Say pi d square upon 4 is a area of cross section. Now we know the area of cross section. Say it is given 50.3. Now pi is say 3.14. D square upon 4. So d square will be 50.3 into 4 upon 3.14, and d will be root of 50.3 into 4 upon 3.14, which will be, you will find 8 mm. So this is how we calculate, or we can have a formula for this. We can derive a formula for this. We can derive a formula for this. Pi 4 4a upon pi is equal to d square, and d will be 4a upon pi. D will be root of 4 times area upon pi. So we take the cross sectional area from here, this table, and multiply by 4, divide by the value of pi. So we get the diameter of the bar. Now mass per meter kg. Once we know the area, cross sectional area, we can derive what is the mass per meter of the specimen. Say 8 mm specimen, if we have 1 meter and cross sectional area is 50.3, we can simply multiply by 50.3 multiplied by 0.00785, we get the mass per meter. So for 8 mm the mass is 0.395. For 10 mm it will be 0.617 kg per meter. For 12 mm it will be 0.88 kg per meter. For 16 mm it will be 1.58 kg per meter. For 20 mm it will be 20.47 kg per meter. For 25 mm it will be 3.85 kg per meter. For 28 mm it will be 4.83 kg per meter. For 32 mm it will be 6.31 kg per meter. This is how, with the area of cross section, we determine the bar of different size, how much it will be weight per meter, and this is the theoretical weight given in the table used for the rolling margin. If we get some bar of less uh, weight per meter or more weight per meter, this is the standard weight with which we compare. So tolerances are given in IS 10790, which was published in 1984, and IS 1786 class 7 also has given for three diameters. If we want to know more, and then we need to refer IS 1984. So as per IS 1786, up to and including 10 mm diabar, the tolerances in the mass, tolerances in nominal mass is plus minus 7% in a batch size, not individual, it in a batch. So it will be plus minus 7% up to and including 10 mm. Over and including 16 mm, it will be plus minus 5%, and above 16 mm, it will be plus minus 3%. Plus minus 3%. With the help of this tolerances, we determine the rolling margin, which we will be studying in detail in the next video. So for this video, we have studied nominal sizes, nominal mass, what is tolerances given the IS code. So we finished. In the next video, we will be taking up a rolling margin, which is very useful for the field engineers. Thank you.